It's very much on now. Maybe we could lower it a little bit, a little more. These things pick up all sorts of things. Is that better? Yeah. Okay, great. Okay, so you're a very, very diverse audience, and I think part of sort of the way modern education works, there's a big spread in whether or not departments teach or provide courses in fluid dynamics. So before I start, let me take a show of hands. How many of you here have already taken a course in fluid dynamics? Oh, wow. Okay, so it's about half of you. Okay, so I'm a little worried this is going to be a slightly impossible task, because if you've never taken a course in fluid dynamics, this is going to go a little bit quickly. And if you have, then well, I hope that I put enough interesting things to at least refresh some of the concepts that you learned, or maybe show you a couple of at least demonstrations that you might have not seen before. So, okay, so for those of you who have taken a course in fluid dynamics, can you help me write down the equations of fluid dynamics? Does anybody remember the Navier-Stokes equations? Well, Vincenzo and I did our undergraduate together, actually, and we both remember this lecturer in electromagnetism, although I think everything he said could apply to fluid dynamics too, who said that after writing down Maxwell's equations, you should be able to be woken up at 1 o'clock in the morning and recite them. So I think the same thing applies to fluid dynamics, to Navier-Stokes equations. So could anybody please help me? So we have a density multiplied by a derivative of a velocity. And then we have a term that looks like this. So what term?
The pressure, the gradient of pressure.
Gradient of pressure, good.
Plus the divergence of the stress tensor.
Okay. Something like this. Yeah. Something like this. And if there's a body force. Okay, very good. How about the other equations? I'm going to put a prime on where? Thank you, Tom. I think Tom's referring to whether or not you include the pressure in the stress tensor, right? So this could be a viscous stress tensor, or you could have the pressure term in there as well. Okay, how about the other equations? Conservation of mass. Okay, so we have dt rho any more? Energy, exactly. Anybody remember that one? This one's a little bit longer, so. Okay. Okay, well, you're jumping the gun a little bit. So we did pretty well. This is what I had before. So it looks pretty good. We got this one. We got this one, although I wrote it in slightly different form. And this finally, there's this third equation over here for the energy.
You want to specify the divergence of u equals 0 for this particular equation?
No, not particularly.
Don't you want then a dilatational viscosity as well?
Yes, exactly. So the question, so David is right. I could have added a term over here, and I was a little bit sloppy. On this side of the equation over here, there is a term which accompanies. Okay, let me fix this by doing this. Okay, where in this term I've included those terms. Okay. So David is quite right. I will revise this very by next time. But in everything which we're going to say, we're going to be taking the divergence to be equal to 0, and we're going to simplify these equations. The point I sort of want to make here is that we have a kind of coupled set of equations which are quite complicated, and these equations encompass an enormous amount of physical phenomena, of fluid flows on large and small scales. And so it's kind of, it's a very, very broad subject, and to try to go through it in 2 lectures is a very, very tall order. So what I'm going to try to do is to build up towards some modern topics. I'm going to start from the basics. We're going to start with looking at these equations and looking at the various terms in them and how we should think about them and how we should interpret them. We're going to think about how we should look at the flow, what the language of fluid flow is. And then we're going to solve some very simple, basic, exactly solvable examples and use that to illustrate what I think are the fundamental ideas which are recurring in fluid mechanics, which have to do with similarity, have to do with dominant balance, and with the sort of spontaneous formation of length scales in your problem. And then we're going to kind of build up towards a picture of fluid flow which is concentrated more on vorticity than any other kind of degree of freedom. And we're going to use that to look at some modern aspects of fluid mechanics, and in particular the appearance of conservation laws which are peculiar to fluid dynamics and have topological interpretations. So we're going to be talking about topology in fluid flows. This will probably be in my seminar after the first 2 lectures. So, okay. So let's see. So, in fact, the way I wrote these equations down, does everybody know what the various terms are in these equations, first of all? So S is the entropy density. Okay. Everybody's familiar with what U is? Okay. Velocity of the flow, very good. And in fact, everybody familiar with what V is? It's also the velocity of the flow. And this is a common problem in fluid mechanics whenever you sort of confront texts or write down your own equations. There's a complete kind of mix of whether people use V or U. So I'm just going to give up on trying to stick to a convention. Whenever you see a V, it is equivalent to a U, and it means the velocity of the fluid. Huh? That one you're going to have to distinguish. Okay, how about the other terms over here? So rho is the density of the fluid, very good. And nu is the viscosity of the fluid. Kappa, the heat conductivity of the fluid, very good. Okay, good. So is that better? Yeah. Okay. Oh, I think it's low on battery. It's gone red. Anyway. Okay, so what I'm showing you over here is a kind of classic picture of fluid flow. Okay, it's a picture made in the lab by injecting. What you're looking at is an object. It's an object that's wing-shaped, and it's sitting inside a wind tunnel, and then, in fact, a water tunnel. And then there's a fluid flowing past it, and some little dye markers have been injected at various points in the flow, and they're sort of going with the flow, and they're showing you the flow. Okay. Yes? How big is this? This I actually don't know, because I didn't take this video. Okay. The fluid is water. My guess would be it would have to be something on this sort of scale, but I don't know, because actually that's a very good question. I didn't take this video.
What's the line?
So what are the lines? The lines in this case, I believe, are hydrogen bubbles, which have been injected by electrolysis upstream by doing a little bit of electrolysis in the flow chamber upstream of the flow. Okay. So there's kind of two ways in which you can think of this picture over here. One way in which you can think of this picture over here is that these lines. So what are these lines showing you? Actually, let me ask you, since we have some streamlines. Okay. So what's a streamline? What? Okay, that's interesting. Okay, so I'm getting two answers. Okay, and that's because there are two answers. And a green light has appeared, and I hear myself. Is that better? Yes. Okay, let's try with this. Okay, so there were two answers basically, right? And one answer was that you were looking at the paths taken by little blobs of the fluid, right? And you put a little blob in here, and it takes this path over here. And the other one was the idea that these lines are showing you a snapshot of the velocity. Okay? In other words, if you asked what the fluid velocity was at every point, it would be tangent to these lines. And if these lines weren't sort of continuous, you'd also be able to get some feel about the magnitude for the velocity. And both those pictures, when you have this kind of steady flow, are completely equivalent. So they're both correct answers. Okay? However, when you have unsteady flow, if you have a flow which doesn't just sort of sit there and doesn't change in time, then these two concepts become very distinct. So let me show you an example of an unsteady flow. This one was taken in my lab in Chicago by Stéphane Perard. You're looking at little tracers which are sitting inside the fluid now. And instead of moving the whole fluid and the tracers, we're going to be moving, creating an excitation in the fluid and letting it go through. Okay? And the scale of this is about this much. Okay?
So is this a viscous fluid, or
This is water. You're looking at little tracers inside water. The scale of this excitation that you saw is about this big. Okay? And so now what we can do is we can take our little tracers and we can draw and try to produce kind of two different types of image which capture these two ideas of visualizing a flow. Okay? And the first one we can do exactly the same essentially as we did in the previous video. We can just add up all the frames from this movie. So we're going to be able to see the entire path taken by all the little blobs inside the fluid.
The excitation was a little rotation on the left-hand side, or what was the nature of the excitation?
Well, we're going to find out by looking at it.
But did you know that you put in a propeller, or you want us to back that out?
We're going to back that out, but I know exactly what I did. Yes. Well, what Stéphane did. So I think I know exactly what he did. Okay, so this is the same picture as we had before. Okay? And what you can see is that with this flow, which is sort of varying in time, this is it's a very messy picture. It contains some very useful information, but it's sort of a messy picture in this particular case. Okay? Another picture we could have taken is by taking that video, and instead of showing the trajectories of the particles for the entire video, just take differences at any one moment in time. So we're going to try to measure the velocity field by blurring the image over a short interval in time. And if we do that for a particular moment in the movie, then we get a very clear sort of picture of what's going on. And this picture over here is telling us the velocity of the fluid at any point inside the fluid for a particular kind of moment in time, or around a particular moment in time. And when you sort of look at this picture, it sort of becomes quite clear what type of flow we were looking at. In this particular case, we were looking at two vortices, or a cross-section of a vortex ring, kind of flowing across the tank. And we're going to be coming back to this a lot. Okay, so. From this picture, no, you can't. It could be going either way. Oh yeah, it's going this way. Okay. Okay. So we have these two kind of ways of kind of thinking about these flow lines, but they're in fact not just kind of two ways of visualizing a fluid or looking at a particular flow. They're kind of two ways of thinking about fluid mechanics. They're two sort of philosophies when you're sort of writing down equations and setting them up. Okay. And we're going to explore. We're going to now look at the Navier-Stokes equation under these two philosophies and kind of think about what the various terms mean. So this is sort of a streamline. This is a sort of plot of the velocity field, and the previous example, or an example like this, is representative of a path line. And later on, if anybody's interested, or in the lecture notes, I will give a couple of examples where you can have flows where there's a dramatic difference between these two sets of lines. Okay. But I don't want to get into that now, I think. So let's see. Okay. So okay. So what we've looked at is so far is we've looked at how to think about this U term. Okay. So we've got an intuition about kind of how to think about the V or the U term in this equation over here. But what we also have in these equations appearing prominently are gradients of the velocities. Okay? So we've looked at kind of the little blobs and their velocities, but we could also have inside our flow kind of distortions that occur inside our flow. Right? So in particular, if we tried to make an image of a flow, right, where instead of considering little points or points which are aligned with the streamlines, we put little blobs which have some shape to them, okay, then we can see immediately that a flow doesn't just sort of carry the individual points around, it also kind of distorts any extended object inside the flow. And this distortion happens anytime you have a gradient in the velocity of the flow. Okay, so let's think a little bit about how to kind of model or think about these gradients. Is there a, okay. So these videos are, some of them are on YouTube. The ones taken in my lab are not yet on our YouTube channel, which doesn't exist yet, but they will be soon. So you'll be able to have access to them. Okay. So if we think about kind of a flow like this was a flow just like the one before, where there's a flow kind of going over here, except now our kind of flow chamber has a constriction. It narrows, so the flow picks up a gradient. We can try to capture the kind of deformation of these blobs by thinking about the gradients in the velocity. Okay, so
those are translation invariant in the direction perpendicular to the stream.
No.
So then, what is the height relative to the width?
What is the height?
Between two parallel plates.
Oh, you're asking.
Third direction.
Oh, I believe the third direction is vertical. So you're looking at a channel that's going along like this.
Okay.
And there's no significant, sorry, I was thinking of the wrong gradient. There's no significant gradients in that direction, out of the board.
Okay.
Yes, but there are clearly gradients in the board.
Right, which means that the chamber itself is quite extended in this
Yes.
particular direction.
Exactly.
Thank you.
Exactly.
That was true for Fred Abernethy's airplane wing as well, I guess.
Yes. 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 The other way of trying to get a two-dimensional flow is to have a soap film and something very, very thin. But those can be tricky to make. Okay, so if we can now go and draw our kind of streamlines, our local velocity vector. I should draw these sort of, if we think about these two paths over here, we have a local velocity vector at these 2 points. And we can consider two neighboring points inside our fluid. We'll call them point 0 and point 1. Okay. And so the point over here, which I've called x0, a moment of time later is going to move, and it's going to find itself at x0 plus v of x0 times delta t. Okay. And our other point x1 is going to go to x1 plus v of x1 times delta t. Okay. Now if I consider these kind of 2 points being, if I imagine that they're close by each other, right, and I call this kind of separation vector delta x, okay, then I can in fact think of the velocity at point 1 as just the velocity at point 0 plus delta x dot the gradient of the velocity evaluated at x0. Okay. So if I include my delta t term over here, what I can see is that basically what happens is that my separation vector delta x goes to itself plus, I'm going to write this as delta xi plus dj di vj times delta xi. Okay. In other words, my gradients in my velocity represent a simple transformation which deforms any kind of lines joining two points in the fluid. Okay. And let me see. This is my attempt at following David's advice. Yes, here we go. Okay. So what we can think of this as a sort of deformation of the coordinates in our fluid. Okay, as equal to the identity plus di vj times our separation vectors. Okay, and just as Tom did the other day, so this is kind of the object that contains all the information, it's very useful to write this object in a slightly different way. So we're going to write it as di vj is equal to, okay, we're going to take 1/2 di vj plus dj vi, okay, minus 2/3 delta ij div v plus di vj minus dj vi plus 2/3 delta ij div v. Yes. Am I missing a factor of 2 somewhere? Okay, this is just literally adding and subtracting terms to our matrix. Okay, this is something that Tom did the other day, but I heard there was some kind of sort of questions about how to interpret this correctly, so I thought I would address it.
You did that to basically make that very contrasted.
Okay, so why have I done this? What is the meaning of these 3 terms? Exactly. So there's one interpretation of why I would do this, which is that they transform differently under rotations. Okay, so you have kind of different invariants under rotations. But really, there's another kind of reason to do this, which is that these 3 terms correspond to the kind of physically different ways of moving of the fluid. Okay. So the way to kind of think about that is to consider the effect of each one of these 3 terms on a little sphere inside our fluid, and see kind of what each term does, how it deforms the fluid. Okay. So let's consider, first of all, the last term over there. Okay. So we have our transformation is the identity matrix plus a symmetric matrix, okay, or tensor, which has trace. And in fact, it's just proportional to the identity. Okay, so in fact, I could think of this as simply 1 plus some transformation times the identity. Okay. Yep. There's a what? Sorry. Am I missing something? Yes. Well, in this case, I haven't really put any indices, so I'm going to. Oh, yes, there's a delta t multiplying the transformation. Yes. The last one, I think you're right, should be 1/3 because of the half over there. Yes. Okay, thank you. So if we think about that last term of what it does, okay, it takes every coordinate and it basically expands it. Oh, sorry. Make it a little bit bigger. Okay. Okay. So I have the identity times 1 plus epsilon. Okay, so if I consider what this does to an infinitesimal sphere or a little sphere of radius a, okay, then this sphere is basically going to be uniformly stretched in all three directions. Okay, so the volume, which is 2/3 pi cubed, is going to go to 4/3 pi cubed. Okay, is going to go to 4/3 pi cubed times 1 plus epsilon cubed, right, which goes with 1 plus 3 epsilon. Okay. So what this term here corresponds to is a kind of general stretching or expansion of the sphere. Okay. Now this is the last term. Okay. The first term, okay, is a symmetric traceless tensor. Okay. And this can be rotated always to have a form which is, so if I write it over here, so this is term number 3. Okay. And this is term 1. Okay. This first term can always be rotated to look like this: 1 plus epsilon 1, 1 plus epsilon 2, 1 minus epsilon 1 minus epsilon 2. Okay. Yes? Huh? This isn't traceless, but it's 1 plus a symmetric traceless tensor. Yes. Okay.
I'm just not seeing how this corresponds to term 3.
You're not seeing how this corresponds to term 3. Term 1.
Oh, the first part labeled term 3.
So term 3 is a number, which is the divergence of the fluid, times delta ij, which is just an identity matrix. So the divergence of the fluid times delta t is a small parameter, epsilon, and so it's just proportional to the identity. Does that help? Okay. Okay, and the first term can always be cast in these terms. And if you think about what's going on, right, how we're transforming our kind of sphere, right, we have if we think of these as being positive, we have a little bit of an expansion in the x direction, a little bit of expansion that could be different in the y direction, and then we have a little bit of a contraction in the z direction. Okay? So if these two epsilons were the same, we'd be taking our sphere and we'd be taking it to an ellipsoid. Okay, so this is kind of shear transformation. And in 2D, you saw this, Tom and Vincenzo talked about this. This would correspond to a transformation that looks like this. And the reason that we went to the trouble of sort of subtracting off this term from this term over here is because then this term over here, if we multiply these three, which are expansion factors, right, to figure out the transformed volume, we're going to have an epsilon 1 and epsilon 2 minus epsilon 1 minus epsilon 2. So it is a volume preserving transformation. Okay. And then finally, we have the third term, the middle term. So term 2, okay, which is an antisymmetric term. Okay, and so by some kind of combination of rotations, we can always bring this to a form that looks like this. Okay. Plus, there's always a 1 plus this. Okay, and so this you'll recognize as a rotation of the fluid. Okay, so in fact, the last term over here, since it's antisymmetric, we lose no information. Okay, if we contract it with an antisymmetric tensor, and we can use that to define our vector omega, which represents this rotation as epsilon ijk dj dk. So this last term over here corresponds, in fact, to rotations. So let's, and it's also volume preserving. Yes?
So can you always assume that divergence of the small?
Can I always assume what, sorry?
Can you always assume divergence of V is small because here you have assumed it to be small, right?
Well, okay, so that's the same comment that came before. There's a delta t, because we're considering a infinitesimal displacement in time.
Okay, but I mean still, but I'm saying like
Yes. Yes.
In such a case, divergence of V will be infinity, right?
Well, it will be large, not infinity necessarily. And so if my epsilon is small enough, I'll be fine.
Okay.
But the divergence of V for compressible fluid is
For an incompressible fluid, it's 0. Yes, and we're going to make that assumption in a minute. So let's just look at an example. Is this too slow for everyone, or I'm sort of trying to gauge the... Yes?
fine.
It's fine. So term 2 is the sum of 1 plus a traceless term. Oh, yes. Oh, it should be traceless. Yes, yes. I'm sorry. Yes, you're absolutely right. Yeah. Okay, so let's look at these three terms. Let's look at a couple of flows, right? And let's calculate these three terms and just kind of compare them with our intuition. And we seem to have lost all our visualization, which is key. Does anybody have a power supply for a MacBook? I think I ran out of juice. Let me see. I think I have one. Where?
Yeah, those two sockets on that.
Two sockets on the black thing. Oh, here we go. Okay, fantastic. Okay, whilst this comes up, let's consider. Okay, I'm going to show you a picture of a flow like this. But let's consider a flow that looks like this. Okay, so what I'm drawing over here, arrows proportional to the velocity. Okay, this is the y direction. Okay, so I'm going to say that u in the x direction is proportional to y. Okay, and so now what we can do is we can compute, well, first of all, the divergence of u, and this way is equal to 0. Okay, so there's no expansion. Okay, and then we can compute our matrix. Okay, dx vx, okay, dy vx, dx vy, dy vx, dy vy. Okay, and this comes out to be, okay, so dx vx is 0. Okay, dy vx is equal to alpha. Okay, and then our other two terms are going to be 0. Okay. Okay, so this is just the matrix. This is just the I Vj. Okay, with I and j equal to x and y. Okay, and we've just computed it for this flow over here, and it comes out to be this matrix over here, which we can write as 1/2, okay, of 0 alpha minus alpha 0 plus 1/2 0 alpha alpha 0. Okay, and so what we can see is that this flow contains two kind of these elements. One element is a shear. Okay, and that's sort of easy to see. If you imagine drawing a little blob over here, it would be shear distorted, like the video that we saw before. And the other one that it contains is a little bit of rotation. Okay. Okay. Another kind of flow that we can consider, that's a kind of canonical one, is a purely rotating flow. Okay. So we can consider a flow where the velocity, all the streamline's a circle, it's a steady flow, and the velocity is proportional to it's a solid body rotation flow. Okay, I'm going to show you a picture in a moment. And the velocity in the is proportional to the radius, and it's in the phi hat direction. Okay? And so such a flow has Vx equal to minus omega times y, and Vy equal to omega times x. Okay, and what we can do is we can go and can compute these three terms over here. And what we will find, you can do this as an exercise, is that the divergence is equal to 0. So there's no expansion. Okay? And in fact, there is no shear component. Okay? And this is in fact the only kind of component which we have, if we calculate di vj, is a pure rotation. Okay? So a flow like this corresponds to pure rotation. Okay? So in fact, if we take such a flow, so here's an example of such a flow on the left, and if we place a little tracer inside of our flow, okay, we see that as it follows the flow, the tracer simply rotates. This is the only component of the flow. Okay? Another canonical flow to consider is the flow which I'm going to show you on the right. Okay? And this is a flow where the velocity, it still has the same streamlines, okay? And the velocity is proportional to some number over r in the phi hat direction. Okay? And so our Vx and Vy are now proportional to minus gamma over r squared times y, and this is gamma over r squared times x. Okay? And you can compute the kind of invariance of this flow, and you'll find that the divergence is equal to 0 again, so there's no expansion or anything like that. Okay? You'll find that the shear component, okay, is non-trivial. So there's a strong shear component, and you'll find that the rotation, so omega, is equal to gamma over yes, the rotational component of this flow over here is in fact equal to 0. Okay? I was going to go through the algebra, but I think we have a little bit of time, so I'll leave that as an exercise. Okay? And the shear component, right, so the magnitude of the symmetric traceless component of this is non-zero. Okay? So it has gamma squared plus 5 times. I'll leave this as an exercise. Okay? Symmetric traceless tensor. So this is term number 1. I should call it 1. Okay? And the determinant of it is this. It changes in direction, so it's not very instructive to write it down in that way. The surprising, well, at least the feature, one of the things that makes this a canonical flow is that just like this flow over here, all the streamlines are circles. Okay? And so you might have expected there to be a rotational part to the flow. But in fact, if you simply take these velocities, right, and simply compute the curl of the velocity, you find that it's equal to 0. This is just a useful exercise to go through. Okay? And so this is surprising because we have this rotational flow, okay, but in fact we're saying that there's no rotation. And that's because there's an important distinction to be made. Everything which we're saying is local. Okay? We're talking about the local rotations of blobs that move with the fluid. So in fact, if we take this flow over here and we put a little tracer to detect whether there's rotation, the tracer follows the flow, okay? But it doesn't rotate. It purely follows the flow without any rotation. Okay? So you can have kind of, flows that rotate globally. The strain tensor, okay, our gradients of the velocities only tell us about what is going on locally. Okay. Interesting. Oh, okay, great. So are there any questions so far before we move on to our Navier-Stokes? Okay, so what we've done is we've sort of taken our Navier-Stokes equations and we thought about how to think about gradients of velocities, gradients of v, and how to think about the velocity. And what I want to do now is sort of turn to the other terms in these equations and think a little bit about how we should think about the equations themselves, what they mean. Okay. So that's going to stay there. Okay. And remember, before we kind of drew this distinction between path lines and streamlines, okay, and these two philosophies. What I'm going to do now is sit in one of these philosophies, okay, which is the streamline philosophy. It's the philosophy where we kind of consider, we sit in a particular place in the fluid. We don't move along with the fluid. We sit somewhere and we consider what's coming in and what's coming out. Okay? And the kind of key kind of idea in this case, that what then these equations become about are tracking the kind of the inflow and outflow of stuff. Okay? And what I mean by stuff in this case is not just little blobs of fluid, but it's a sort of set of conserved quantities. Okay? So in fact, if we sit at a particular place in the fluid and we consider what's coming in and what's going out, all these equations over here become one equation, which is dt of some number plus the divergence of a current associated with that number is equal to 0. Okay? And this is a sort of familiar, very familiar equation. Okay? If we consider any finite volume, right, or if we sit and we draw any particular sphere or circle in our fluid, it's telling us that the total influx of this number, okay, the rate of change of this number inside this volume is equal, by the divergence theorem, to the integral of the flux of this quantity through our surface. Okay? If we think of this as the surface of our volume. It's a statement of conservation. Okay? And so now, all we have to do in this picture to interpret these equations is to go back and think about what the number is, right, and what the associated current is. Okay? And here we see that there are basically kind of, the current is sort of how the fluid flows, or the quantity flows, and there's basically kind of two ways to flow, if you like, in a fluid. One way to flow is to just move. Right? I'm kind of making my paper, which is a conserved quantity in this room, and carrying it from here over to here. Okay? And so, for example, if I'm asking how mass flows, our first equation over there is d by dt of rho. So we're talking about the mass of the fluid. Okay? Then this term over here has an associated current for the mass. Yes?
Are we assuming that everything that's flowing is incompressible?
No. No, we're not. We're going to be doing that later. But for now, we're treating this generally. Okay. So if I'm thinking about mass, which is a conserved quantity, and I want to know what the current associated with mass is, well, mass, sort of moves from one place to another, right? And so the natural current for mass is to have the mass density times the velocity. Okay? And in fact, if I put that in here, then I obtain the equation d by dt of rho plus div of rho v is equal to 0. Okay? And so now we know, we sort of knew this before, I'm belaboring this point, but for a reason, that the first equation has a simple interpretation, which is the conservation of mass. Okay? Okay. But mass is kind of a scalar quantity, so it's this was very familiar, and this was something that we were all kind of immediately, probably most of you looked at this equation and said, that's conservation of mass. What's this guy going on about? But in fact, what I said is that this number can be any conserved quantity, and so it could also be, for example, the momentum of the fluid. Okay? And so now we have to ask about the ways in which the momentum inside the fluid can flow. And so our left-hand side becomes d by dt, okay? And our momentum is rho v. Okay? And now we have to consider the various ways in which the momentum can flow. Okay? And this kind of the simplest way in which the momentum can flow is, again, by moving. Okay? And so what should we do? Well, we want that this plus div, so I'm going to put an I over here. So this is going to be div j jvi. The current of rho vi, so it has an index, okay, has got to be equal to 0. And our guess for the current, for the momentum of j rho vi, is going to be the natural one, the same one that we made over here. We simply multiplied the mass density times the velocity. And so now what we're going to do is we're going to multiply the mass density, okay, which is rho, the momentum density, which is rho uj, times the velocity ui. Okay, and this is the way in which momentum moves, simply by moving, by taking a blob of fluid that has momentum and moving it. Okay, so this is our current over here. And so what we can do is we can plug our current over here. Notice our current over here has two indices. Okay? So I'll give it a name. I'll call it a candidate. I'll put triple dashes here for Tom because it's a sort of uncanonical way of expressing it. It has two indices, pi ij, and it's equal to rho ui uj. So if I take this current and I just put it in my conservation equation, right, then this is going to become di of rho ui uj. Okay, let me take this up. And I can naturally break this up into two parts. Okay, and so I have dt of rho uj. Okay, I'll write under the shadow for the other terms. Okay, so this is naturally equal to dt of rho times uj plus rho dt of uj. On this side over here, I have two terms. So this is going to be di, okay, of rho ui times uj plus rho ui di of uj. Okay, and you'll recognize immediately that this part over here has a dt rho multiplying uj, and here we have a div of rho v multiplying uj. So by the conservation of mass, we can just eliminate these, and what we're left with is rho dt of uj plus ui, basically u dot grad of uj. Okay. So if we, so this was just simply taking mass, momentum, and moving it in the same way that we took mass before and moved it with the flow. Okay. And what we see is that the term that this corresponds to has this form over here. Okay. And this is an important form. So in fact, even gets a name. It's d by dt of uj. Okay. And it's a term which you'll recognize in a lot of the equations. Okay. So we have over here d by dt of u plus u dot grad. There we have d by dt plus u dot grad. Okay. So now we know how to think about that term over there. In fact, interestingly, okay, so that's basically all I have to say about kind of these conserved quantities flowing or moving by moving. Okay. But there's a second way in which conserved quantities can move inside a fluid, and that comes from the microscopics of the fluid. Okay. So these fluids are kind of fluid because they can move around because they have entropy. So there's a kind of thermodynamics associated with it. There's a microscopic part of the fluid motion. Okay. And so this also provides a way for this conserved stuff to move around. Okay. So for example, our momentum could diffuse, or we could think of if we put some dye inside of a fluid, of our dye diffusing. Okay. So we need to sort of start to incorporate the microscopics. And so interesting, in fact, one of the kind of first things you can do when you start thinking about trying to incorporate the microscopics is think a little bit about this term over here, which we took over here to be a macroscopic term, sort of average term for the blob, and ask whether, well, if I really kind of take my fluid and I kind of go all the way down to the atomic size scale, then my velocities can fluctuate. Okay? So maybe I should go back and I should revisit this current over here from the microscopic point of view and think a little bit about whether I'm missing something when I'm doing my averages. Okay? So let's do that. Are we at the break time? I'll be at a natural break time in a couple of minutes. So I'll take it then. Huh? You need me to lift. Oh, sorry. I'm going to provide notes when I figure out what we actually cover.
So the conservation of momentum is capital D dt of uj equal to 0, right?
The conservation, yes. Okay.
That will only
Well, we're getting to the stress part, right? So everything else comes from the microscopics of the fluid. Okay? And the first place in which the microscopics of the fluid come is from, if you imagine taking this fluid and really kind of zooming in so far that you're looking at the motion of the individual molecules, in which case we have to rethink about our current, J, our current pi ij, which is rho vi vj. Okay? And now we have to suppose that we have kind of our v's are really equal to the v that we considered before, which is sort of like a time averaged velocity. Okay? So this is equal to the average velocity plus some fluctuation term, which we have. Okay? And if we substitute this back in here, then we find that this is rho vi plus delta vi times vj plus delta vj. Yes?
So spatial fluctuations over time?
Velocity fluctuations. So we're talking about velocity fluctuations, and we can now try to take the time average of this to see if we miss the term. Okay? And if we do that, we're going to get 4 terms. We're going to get our average velocity terms, which is what we had before. So we're going to have rho vi vj, both time averaged. But in addition, then we're going to get terms which look like a number, v, which is just a number, times a fluctuation, which under averages goes to 0. But we also get a quadratic term, which was delta vi, delta vj. Now, fluctuations, for thermodynamics are sort of considered independent in different directions. Okay? So there's going to be no off-diagonal terms coming from this term over here, right? But you are going to get on the diagonal delta ij, a term which comes from the fluctuations squared. Okay? And if we think about what that corresponds to in macroscopic terms, it's corresponding to a pressure. Okay? So we've kind of gone from taking average blobs of fluid with their average quantities and moving them around. We've zoomed into looking at the microscopics, and the first thing that we found is that our momentum transfer equation was missing a term. And in fact, this term, which comes from the microscopics, is just the pressure. And so now we can go back, and we have an interpretation for this term over here. Okay? The gradient in the pressure, if you like, has to do with the fact that pressure at the microscopic level is like a form of kind of momentum, which is being transported and advected. Okay? Yes. So this is for an ideal gas. So this is a little bit heuristic. If you want to consider something which is more complicated, okay, then you're going to have to think about the thermodynamics of the fluid carefully. Okay, and your pressure is going to be related to the constitutive equations for the fluid, and it gets a little more complicated. Right? What I'm trying to do over here is really paint a kind of way of thinking about these equations in the form of conservation laws, which include macroscopic average quantities, but also include microscopic quantities. And this is something that, one of the reasons I'm doing this is it's going to come up again and again in Christina's lectures, and I think in John Toner's lectures later in the school, where you really start to now modify the microscopics of the fluid, and you ask what different equations you get when they come out. Okay. Yes? So the argument over here was that if we now think about these as being velocities of blobs that are so infinitesimal that we need to worry about their fluctuations, okay, then we can sort of think about these velocities as a kind of averaged background velocity, which if you average the fluctuations is what remains, and a fluctuation velocity. And then when you multiply these, you get one term which is the product of 2 averages, so that's just a number, okay? And then here you get this term with this term is 0 because the fluctuations average out, and only the fluctuation squared is what's left. So you can think about the pressure as a sort of microscopic momentum conservation term. No, you assume velocities, you assume the fluctuations in the x and y and z direction are independent. Okay. Okay, so great. So that's one way in which the microscopics come in. Okay, but another way in which the microscopics come in is if you ask about the average momentum. Okay? You can ask whether or not these average terms over here, okay, also can somehow diffuse in some sense. Okay? Right? So
I'm not sure how exactly
What's the logic behind this being high pressure? Well, if you're thinking, for example, about an ideal gas, then this is a kind of measure of the pressure. Right? That's what pressure is. It's an average. It's a measure of the kinetic energy, the average kinetic energy of the fluctuations of the particles. Okay. So actually, I think. How are we doing for time? Let me just show you one. Okay, I'm going to show you a video, and I'm going to make a few more comments about a final term in those equations before we take a break. Yes?
So one more question about that being a pressure. So if temperature is 0,
Yes?
you have an ideal fluid.
Yes, absolutely. Except that, as I said, you have to be a little bit careful about fluids that aren't things like ideal gases. Okay, so if you in the other way in which we think about these equations, which we're going to do next, right? Then it's more natural to think of the pressure as a pressure, as a force that acts on little blobs, and a zero temperature fluid will have a constitutive equation which allows the pressure to be non-zero even though the temperature is 0. Okay, so that's going to come in that way over there. Okay, so the last kind of way in which things can flow concerns the average fluid. So I want to show you this video over here where we've taken, there's two concentric cylinders over here, we've drawn a line in them, and what we're going to do is we're going to rotate the inner cylinder. Okay? And what you see happening when you rotate this inner cylinder, right? There's circular symmetry. So all the flow lines, everything which happens, is going to be in circles. So there's no transport by motion, okay, between circles. Everything is purely circular. Okay? But yet what you see is that when you create a gradient in velocity, so when you create velocity by imposing it over here, this velocity, this momentum that you're putting in there, flows across these streamlines. And that's because there's the gradient in velocity. Okay? And the way to think about this, the sort of simplest way to think about this is to take that flow and make it, let's say, parallel plate-like. Okay. Okay, so we consider back, we think about our flow like this. We impose some flow over here. We see that the momentum in the x direction kind of moves across. Right? And the simplest way of coupling these is a diffusive term, which is to have a current of momentum, right? Momentum in the x direction, so rho ux, okay, which is proportional to the gradient in the y direction as a y component, okay, which is the proportional to the gradient in the y direction of the momentum in the x direction. Okay. So now if we kind of generalize this and we add this to our current, okay, we're going to have a current which is we're going to have to add a term to our momentum balance, okay, which is looks like a derivative of the velocity. And this is coming from the sort of diffusion of the momentum across these streamlines. So I think this is probably a good place to take a break. We'll come back in 5 minutes and talk about another way of picturing these flows. Yep.
So I didn't understand how that particular pressure term was going to contribute to the momentum conservation. Like you said, the momentum conservation is incomplete. Right?
Yes.
So how is that added to this equation to complete the momentum conservation?
Oh, because you include the fluctuations, and you see that you get an extra term, right? Because you have di of pij of the momentum tensor.
Right.
So now this has an extra term, which is delta ij times the pressure. So that's going to be minus the gradient of the pressure.
Oh, okay. So you're saying like the pi ij itself is changing.
Yes.
Okay. So
Yes.
so now your pi ij is basically this quantity.
Yes.
And then you put that back. Okay.
Yes.
So bad to say.
Sorry, when you said that this term was 0,
Yes.
weren't you sort of implicitly assuming that you were incompressible because you also have this term, which is not necessarily zero, right? I mean, you said that this was zero.
Yes, d by dt of rho u, yes. No, this plus the other term, which looks like, so here you have a uj, then there's another term which is di of rho ui. Let me write it down here. So you have dt, right, of rho uj plus di of rho ui uj.
Right.
Okay, so here this term is two terms. This is rho dot uj plus rho uj dot. Okay, and this term over here has two parts. It has a di, has di of rho vi times vj plus a rho vi di vj. So if you collect the terms that go with the j, right? If I take this term plus this term, that looks like rho dot plus div rho v multiplied by vj. And that just goes away by conservation of mass.
All right. Yeah. Okay. Thanks.
So when you're talking about the diffusion and momentum, basically, okay, it's understandable that, I mean, is it okay, the velocity fluctuation drives that one, or is it because of the stresses that they would transform after that?
It's the same
It's
thing.
the same thing.
But now there's a stress.
Okay.
It's not an ideal gas anymore.
Yeah.
Yeah.
I mean, basically, I mean, if you have it, for example, between the fluid and the gas, that basically you have the different range of a Schmidt number. That
Yes.
basically,
Then
then
that
you
gets
can
complicated.
basically become the booster.
Yeah.
Okay. Thanks.
Yes?
I think maybe I made a mistake in writing. So this is the current. Is it the y component of the current?
Yes.
And it's equal to something like gradient of this quantities looks like current too. So I don't know if I made it a mistake in writing this.
Well, you're considering now momentum.
Yeah,
So the
consider
quantity is a vector by itself,
momentum.
right? So you're considering the transport of a vector quantity, rho vx, okay, by a gradient in this quantity. So the vector is this way, but the gradient can be this way.
Okay.
I don't know if that helps.
It just seems like there's something missing. I don't know. Okay,
It's
so
just like this. If you think about ink, right? If you think about a quantity like ink, okay,
Yeah.
then you have a concentration of ink,
Yeah.
okay, and this is going to be proportional
To the
right, plus div of j ink.
yes.
So this is going to be j ink
J.
is equal to 0.
Zero.
Okay. Now j is proportional to the gradient of the concentration.
That I understand. Oh, so this. Oh, now I understand. So this quantity is different from. So maybe it's notation.
Yes.
What does this quantity mean?
This is the current of the x momentum.
The current of the x momentum.
So I'm doing dt of vx, of rho vx, that's the x momentum, right? Plus the divergence of the current of the x momentum. And this current is proportional to the gradient of rho vx.
I'm also confused. Before, in the beginning of the class, just say the current is rho vx, rho
I said-
vx vy.
Yeah, but I said there's two ways to think about it. One is moving and the other one is microscopic. So I'm adding the microscopic terms as we go along.
Do you mean they're equivalent?
No, it was missing before.
I mean the current has two parts. One
Yes.
is rho vx, rho vy. Then
Exactly.
there's another. Okay.
Exactly.
So this is phenomenological, right? You assume the current is proportional to the gradient. It's
Yes.
Kind of
So
like
my last question, I'm confused. I was thinking this current, by definition, is this rho vx.
No, because there can be a j in the y direction
Oh, okay.
of rho vx.
Yeah.
Yes. Okay, thank you. I'm going to clarify that.
Are you? Okay.
Hey. Yeah, it's kind of cool, no? Okay, but I'm kind of getting in trouble here. Okay.
The experiment that you showed for two vortices that they were just traveling,
Yes.
you were getting some kind of extension outflow.
Yes.
And I mean, is it possible to also look at them and the strain rate that you were getting basically, and how is that?
Yes.
Is it possible also to generate tooth?
You want to do rheology with it?
Yeah.
Yeah, it's an interesting question.
Yeah.
I haven't thought about that.
Yeah. Because actually, I'm doing with the 4-row mill.
Okay.
And basically the system that we were getting, and now people they're generating with the microfluidic this extension outflows.
Okay.
And they put the DNA in and then stretch it or something. That's crazy. Yeah, that was very nice.
Thanks.
So what Adam was saying though is that you can apparently the road is
Yes, thank you. Okay. Okay, so we should probably at least let me take the first kind of minute to clarify a little bit of confusion about the last kind of transport term that we considered, which was this diffusion of momentum. Huh?
it's a little too empty. Let's get more people in.
Okay. I'm really responding to a question. They might be over there.
So that's why you have to cycle around because you get back to the edge.
Okay.
It looks so fun to do though. And it's so gross because all the time, every time they do it, it just the one sits there. And every lecture just keeps even more.
Already it's going to get wet. Okay, so let's get started again. So what I'd like to do now is first of all clarify a little bit of confusion from the last thing which I said just before the break, which had to do with this diffusion of momentum, okay, in a direction perpendicular to the flow. Okay? So in general, if you think about kind of another way in which microscopics act to move stuff around, then as David kind of very carefully went through in his lecture, right, there's a way of doing this by kind of diffusion, by counting the number of states which you can have in different configurations, and noticing that many more of them involve some kind of spreading. Okay? In that case, it wasn't quite diffusion he was talking about, but it's the same underlying idea. So you could imagine having, for example, a blob of dye inside a fluid. We can put a blob of dye. Okay, which basically I can model by a concentration of ink. Okay, so I have some kind of concentration of ink, C. Okay, and then I can ask, how does this concentration of ink, if I put this blob of dye in the middle of my fluid, change in time? The way in which this changes is that the rate of change of the concentration of dye is again going to depend on the divergence of some current of the dye. Okay? And in general, when we have some kind of diffusion which occurs by randomized collisions, then the current that corresponds to the flow of this dye is going to be proportional to the gradient of the concentration. And so if I want to model the diffusion of my dye, I'm going to get something that looks like this, plus del squared of C. Okay, and this is our diffusion equation. Now, in a similar way, if I have some parallel flow like this, okay, I have my dye, my quantity which is going to be transported is the momentum in the x direction. It's rho ux. So C goes to rho ux. Okay? And I can have a gradient in the y direction, okay, of the x momentum. Okay? And so if I think about this momentum as moving diffusively from one layer to the next, which is what we see happening when we take our when we do a little experiment where we inject some momentum, this in the radial direction, okay, and what we observed is that this momentum kind of moves across these parallel lines. Okay. Then I need to have a current for the x direction of momentum. So I need to have a current, J, for the momentum in the x direction, right? Which is like saying pi, if I call this I, this is going to be pi Ix. Okay. And so the current associated with this x momentum, which is diffusing, is going to be proportional to the gradient of the momentum in the x direction. Okay? And so I can have, by diffusion, a transfer of momentum from one layer to the other. And this is a different mechanism from the one which we considered before. Everything we considered before was momentum simply being advected and simply moving from one place to the other. Okay? And in this case, all the velocity of the fluid is in this direction, and the momentum is diffusing in this direction over here. Okay?
The ninth movie, the rotation is of the inner circle?
Yes. Yes, exactly. Okay. So if we think about what this is going to end up giving us, right, is going to end up giving us a term which is diffusive, right, which looks like, just as we got over here, a term which looked like the Laplacian of the concentration of the dye, we're going to get a term which looks like a Laplacian of the momentum, or at least the velocity. Okay. And as David was saying earlier, I'm kind of assuming divergenceless in doing this. So now we should have, oops, okay. So now we should have an intuitive kind of understanding in terms of transport of conserved quantities of all the terms which we saw inside our Navier-Stokes equations. Okay? And I invite you to go back and look at them and kind of identify all these terms. Right? Very briefly, we have a term that looks like this, dt plus u dot grad of u. And we saw that this was a term. So we have okay. So we had a term which looked like rho dt of u. And this was the rate of change. This came from considering the rate of change of momentum. Okay, we had a term which looks like u dot grad u, and this was the advection of the momentum by the flow. Then we had a term which looked like the gradient of a pressure, and we interpreted this, at least in the case of an ideal gas, as the advection of the microscopic part of the momentum, which we sort of missed by considering time average quantities. And then finally, we can have a term which is diffusive, which corresponds to the diffusion of momentum perpendicular to the flow. Okay? And so this is kind of, in this way of thinking about conservation, flows as conservation of stuff, where these kind of different terms come from. Okay? Now there's another way of thinking about it, which is sort of probably the one which is most familiar, or at least the one which is often given in introductions, which is to instead of sitting somewhere and asking what's flowing in and what's flowing out, to follow a little blob of fluid. Right? And when you follow a little blob of fluid, you can ask, for example, how something in this blob of fluid changes. Right? So, for example, this blob of fluid could have some temperature or some concentration of something, and I want to know how that changes. And so let's suppose that the variable I want to consider is t. So, and this blob is going to move from one time to the next to a new position. Okay? So this property which I'm tracking is going to be at this time is going to be simply t of x, okay, at time 0. Okay? And this is going to become t of x plus delta x, y plus delta y, because it moves, right? Z plus delta z, t plus delta t. Okay? So if I consider just an infinitesimal motion, okay, then I can expand this, and this is going to be equal to t naught, right, plus delta x dot grad times t, evaluated at naught, right, plus dt of t. Okay? And if I think about my delta x's in my little blob that moves, well, delta x is just equal to v times delta t. So it's just a motion. It goes with the flow. Okay? So in fact, I can, I'm missing a delta t over here. Okay? So in fact, I can just rewrite this as v, right, dot grad times delta t of my quantity temperature plus dt of t delta t. And you'll recognize immediately the term that we have is dt plus v dot grad of t. Right? And so that's saying that if there's any kind of quantity inside my little blob, which I'm following, then the way in which this quantity is going to change as I follow the blob is by this derivative over here. And so now if this quantity inside this little blob isn't the temperature, but for example it's the momentum or the energy, then I can go back and think about these various terms as asking, for example, how does the momentum of my blob change? So I can now think of dt plus v dot grad of my momentum. And then on the right-hand side is, well, how does the momentum inside the blob change as you follow it? Well, it depends on the forces that the blob feels. And so now I can think of this pressure term as a force. So it's the differential force that acts on one side of the blob and from the other one. Okay? And I can also have a little bit of the possibility of having a little bit of diffusion out of my blob. Okay? So, you can pick your favorite way of thinking about the equations and your favorite way of constructing the equations when you're dealing with unfamiliar settings, when you're not dealing with a simple Newtonian fluid and you're adding ingredients to the fluid. But these are really two kind of pictures in which you can think about the flow. Okay. So are there any questions at this point before we go on to look at an example? Everybody happy? Okay. Okay, so in general, these equations, the Navier-Stokes equations, are very hard to solve. Okay? Anybody know why they're very hard to solve, or can think of why they're hard to solve? Nonlinear. Very good. Huh? Coupled. That's another one. Exactly. They're kind of complicated, coupled, nonlinear, sort of mixed character differential equations. And so usually you don't get the luxury of solving them, except in very, very specific cases. Okay? So what I want to do now is kind of take one of these very unusual kind of privileged cases in which you can solve them, and we're going to consider a very simple situation, and we're going to solve it exactly. And then we're going to use this exact solution to go back and sort of think about what we could have done if we weren't able to solve it, and what the various terms inside the equations, how they compete with each other, and how we can learn how to simplify these equations to solve them using intuition. And this involves the sort of concept of dynamical similarity and dominant balance. Okay? So the first way to sort of simplify the equations, which we're going to adopt from now on, is to consider our fluid to be incompressible. Oh, it's in the shadow. Man, you get less real estate here. Okay, so div v is equal to 0. So we're going to assume that our fluid is incompressible, okay? And we're going to assume that it's so assuming that it is incompressible and it's simply viscous. And the other assumption which we're going to make is that we're not going to worry about the thermodynamics of the fluid. We're not going to worry about heat generation by friction inside the fluid. We're not going to worry about temperature variations in the fluid. Okay? We're basically going to consider a flow where the entropy doesn't change of any one blob in the fluid. And so what these two assumptions allow us to do is to forget about the mass conservation equation. Okay, that just becomes simply a constraint, which is the divergence of the velocity 0, and to forget about the energy equation. And we're simply left with the momentum equation. And then the problem that I want to consider is a problem which consists of a flow between two parallel plates. Okay. So we have two parallel plates, and we're going to apply a pressure, okay, a pressure gradient, which is oscillatory. So we're going to kind of push and pull and push and pull on this fluid using a pressure gradient. So this is going to go with, I'm going to call it P times e to the I omega t. Okay, where capital P is not the pressure. Should I use a different symbol? I'm going to call it hash. Okay. So we're applying an oscillating pressure gradient of strength hash to this fluid. Okay. Symbols are not my my forte. Okay. And so what's going to happen? Anyone? You know the equations, huh? It's going to slosh back and forth, right? Okay. Now, what can we say about that? Yes. I have two plates. The plates are stationary, and I'm oscillating the fluid back and forth. It's a homogeneous pressure gradient. Yes, you're pushing and pulling with.
Can you show us some little bit of detail?
Oh, this is a thought experiment. You can solve this one. No, but you could imagine taking a microfluidic channel, for example.
Is it like
right?
a speaker?
Yeah, you could imagine something like that. You could imagine taking a microfluidic channel, right? So you've made your very, very long, thin microfluidic channel, and literally applying a pressure difference from one end to the other. Okay, but you have a fluid which is incompressible, so the speed of sound is sort of infinite. So your pressure goes all the way through the fluid, and you have a pressure gradient, which results from this, and your fluid sloshes back and forth. Okay. So what's going to happen is that the fluid is going to slosh back and forth, and it's going to slosh back and forth just in the x direction. Right? If there are no pressure gradients in other directions, then there's no reason for it to slosh in any other direction. Okay? So in particular, there's going to be, let me see here. So our U's, our V's, okay, that our velocity, okay, is going to be proportional to Vx 0, 0. And so what we can see immediately is that if we consider we put this inside our nonlinear term, which is a term that we're already worried about because it's one that makes these equations hard to solve. If I consider what v dot grad v looks like, right, then it just looks like Vx dx of Vx 0, 0. So the only term which I have coming from this convective term is dx of Vx. Okay? But if I think about this equation over here, right, and what this equation over here tells me is that dx of Vx plus d other stuff of 0 is equal to 0. So dx of vx is equal to 0. Okay. So simply by having this kind of highly symmetric situation, we're able to ignore this term over here inside our equation and simplify our equation. Okay. So our equation now becomes rho d by dt of ux, okay, plus a term which went to 0, which is our nonlinear one, is equal to minus our gradient in pressure. So in this case, it's going to be, I'll just put it as dp dx, p by dx, plus we have our rho nu, okay, d2 vx, and the only way in which the vx can sort of vary in this context is in the y direction. So this is going to be by dy squared. So is everybody happy with this? Okay. So yeah?
Could you just repeat the argument for why vx is 0?
Okay, so by taking this highly symmetric situation, where we only have velocity in this direction over here, right, we can reduce the nonlinear term to simply vx dx of vx. That's simply because v dot grad is just vx dx, okay, and this is the only non-zero term. Okay, but if we consider our velocity, right, then we have only an x component. So when we take the divergence of our velocity, we know that dx vx has got to be equal to 0. And so that kills the nonlinear term. Yes? This is dy squared. Sorry, I'm missing a little bit of real estate. Yes? Oh, well, now we're going to, exactly, so good question. So we've reduced our equation by making these simplifications. Now we have to worry about our boundary conditions. So what are our boundary conditions?
If it's incompressible,
Yes.
pressure, there's some constituent relation between the pressure and density. The density is constant.
Yes.
So should I think of it as only, you're imposing, well, how do you impose a constant gradient pressure?
I mean, usually if you put a gradient in pressure and you have some resistance to the flow, then you get a gradient in pressure.
Is it a difference in pressure between the left and the right?
I mean, it's a dynamical situation, right? So the fluid is constantly accelerating because you're going back and forth. And so you have a gradient in pressure which pushes that acceleration in the inertial case. And in the non-inertial case, it's viscosity that's balancing the pressure gradient. It's because it's an oscillatory flow. I think maybe that's the confusing part. Okay. Everybody happy with these simplifications? So, yeah? You can have a profile for the x velocity that can vary in the y direction, but you don't have a y velocity. Yeah. So in fact, that's a good point. Just to make this, let's make this absolutely clear. Ux, right, can be a function of y, right, and it can be a function of t. Okay. And what we know is that we want the boundary conditions, right, which we're going to take are the boundary conditions of the Navier-Stokes equation, as that there's no slip, there's no velocity tangential to the boundary at the boundary. Okay. So we want the ux at y equals to plus or minus a over 2 is equal to 0. Okay. So okay. So now what we have is basically a linear differential equation. Okay, and we're driving it with an oscillatory flow. So we expect the response to be oscillatory. So we can take this. We can sort of take this to be a ux of y and omega times e to the I omega t. Right? We're just putting in a guess, which is that our flow is going to oscillate because the equation is linear. It's going to oscillate. And so we could spend some time sort of trying to constructively solve this, but in fact, The only way I really know to solve differential equations is to know the solution and verify that it is the correct solution. So I'm going to give you the solution, and we're going to prove that it is the right solution. Okay, so the equation is a kind of a familiar one. It's a diffusion equation, right, with a forcing term. Okay, and the solution in this case that satisfies the boundary conditions is u of omega and y is equal to I over rho omega, our gradient, which is going to be hash in this case over here, times 1 minus cosh of ky over cosh of k a over 2. Okay, I is I. Yes, I is equal to the square root of minus 1. Okay, and we're obviously taking the real part of all these things. Okay, in the end, but it's linear, so we don't need to do that at this stage because we've killed a nonlinear term. Okay, and k works out to be the square root of I omega over nu. Okay, so this is the solution to our flow. And actually, given the amount of time we have, I think it's more instructive to look at this solution, right, and deduce things from it rather than kind of prove to yourself that it's a solution. This is something you can do this afternoon. In fact, I'm almost out of time, so let me seek my attempt last night at plotting the solution. Here we go. Okay, so oh wow, look at this, it worked. Okay, so can everybody see this? Okay, that's a little bit better. Make this a little bit bigger. Okay, good. So I've taken this solution, which I've written down over here, okay, which is the solution we just wrote on the board. It's e to the a omega t times our solution over there. Your exercise is to check that this is the solution to this differential equation, okay, with the satisfying the appropriate boundary conditions. And what we have to do now is we have to plot it, right? We have to choose some values for the parameters. Okay? And so the parameters that we have are sort of the density, okay? We have the frequency, we have the width of the channel, and we have the pressure gradient which we apply. Okay? Now these parameters kind of don't appear arbitrarily. They appear in kind of groups. And one group of parameters which appears is a squared omega over nu. Okay? So I can vary these in different ways, okay? But essentially I'm varying really a group in this case over here. Okay, and the other one is the pressure gradient compared to the density. So you know, physically, can you think about what this kind of parameter is telling us? So high frequency, right, is equivalent to small viscosity. That's how I would think about this. So I can make the viscosity small or the frequency high, right? And I can also, somehow this ratio of viscosity to frequency is being compared to a length, okay, which is the width of the channel. So these are the three parameters. This is the way in which these three parameters comes bunched in this solution. So really, what I'm going to do is I'm going to set a bunch of them equal to 1. So I'm going to set a equals to 1, nu equals to 1, rho equals to 1. I'm going to adjust the pressure gradient just to get a good plot, okay? And I'm going to vary, say, actually no, I'm going to fix omega and I'm going to vary nu. I'm going to vary the viscosity, okay? But really, I could have varied any one of these. So the first case I'm going to consider is the consider.
Sorry, maybe you said this when I was out, but that's the Reynolds number.
Not exactly.
Well, a times omega is the velocity. A is a length.
Yes, yes, you're right. It's effectively a Reynolds number. It's a comparison in the oscillatory flow. It's like a comparison between the time for the. I mean, the way I think about this number is the time for the boundary layer to diffuse. But I'm getting ahead of myself. Okay, compared to the width, diffuse the entire width of the channel, compared to the cycle time. So indeed, the boundary layer thickness is related to Reynolds number, but I think of this more in this sort of transport type way of thinking about it.
Yeah, then no inertia can.
Yes, this is not flow past the plate. It's an oscillatory flow. So, yeah.
Not really.
Yes, but we're jumping a little bit ahead. That's the next concept which we're going to get to. Okay. Half of you know this, but half of you don't. So, so we've taken, and I've plotted, in this case, I've taken the viscosity and I've put it also equal to 1. Okay? And the result is this. So rotate this picture 90 degrees, and this is the velocity profile. This is one boundary, this is the other boundary, and this is the velocity profile of the fluid inside the channel. Okay? So we have this flow, which is kind of faster in the middle, goes to 0 at the edges, and oscillates back and forth. Okay? But now what I can do is I can start to reduce ask what happens if I start to reduce the viscosity. Okay? So in this case, I've put the viscosity equal to 0.01. And what you see is that the profile of the flow changes quite significantly. Okay? So the profile of this exact solution kind of changes, and it starts to pick up kind of these funny gradients. It looks uniform in the middle, okay? And then it has these kind of two wings at the edges. And then... Huh? Yes, there's something like that. But, well, it's not steady, so you don't need to have a backflow. But you have the kind of signature of the onset of it. Okay, and finally, I can take the viscosity to be very, very, very small, right? And plot this flow. And what you see is that what the flow has become is a completely uniform velocity across the channel that just sloshes back and forth. Okay? And so if you think about this, what we're seeing is a kind of transition in the character of the flow, right? This first flow over here this last flow over here is a flow at low viscosity, and it is the flow that you would get approximately, at least for most of the channel, if you neglected completely the boundary conditions. You just thought of this thing as something that can slip freely, and you just did F equals ma for the mass of the fluid. So you're pushing it, and it's just sloshing back and forth inertially in response to your pressure term. Okay? And then as we make the viscosity bigger, you see that there's a change in the character of the flow. And this looks nothing like our flow, which is just a plug moving back and forth. It looks like a flow which is heavily constrained by the boundaries. It's in fact 0 at the two boundaries, and has a strong variation inside the flow. And the difference between these two flows comes from the difference in the importance in these two flows of the inertial terms, which is rho d by dt of u, compared to the viscous diffusion term. Okay? And that is kind of something which is the, basically for those who know, I'm trying to introduce the concept of a Reynolds number. And for those who don't know, that's what's coming next. Yes?
So you made the laminar flow assumption, say
yes.
y equals 0.
Yes.
But doesn't that assumption break down if you reduce the viscosity too much?
We're going to come to that. Yeah. Yes?
I don't understand why if you increase the viscosity you have those kind of maximum.
Yes. So there's different ways to think about that. One way I would think about that is that imagine I have a flat plate and nothing above it. Right? So now I'm just oscillating my flat plate. I'm taking the fluid to slosh back and forth. And the fluid can exert a force on the next layer of fluid, but it also has some inertia. So I could imagine something like a wave going away from my oscillatory motion, except I have a lot of viscosity, which is also what allows the thing to go in the first place, so I'd expect this wave to be damped. So the way I think about that oscillation is sort of like something like a shear wave which is being damped. Another way to think about it is that you have a diffusion equation. You have a diffusion of momentum, but you're pumping it in with positive and negative momentum. And so, as these two catch up to each other, you're going to get an oscillation. Well, if you have a wave, right, you're going to overshoot and come down. Okay, I think I'm over time already. So if there are more questions, I'll take them. I can take them in the break. But
What about the demonstration?
Oh, what about the demonstrations? The demonstrations are going to come next time.
turbulence
Yes.
that you get at a
Sure.
very high Reynolds number. With the other question, with the sort of the peaks that you got near the thing, they sort of look like this, right?